And the best phase is one single phospholipid or a mixture of two that is in the liquid disordered phase. Mainly there is quite high fluidity and very large free volume, which is opposite to what we want in the doxil. So again, you can see the phase transition of the lipid we use is in this range, 24 to 37 degrees. You have to be below 37 degrees, so the lipid will be in the LD phase. That's a very, very important. Again, we use the multilamellar liposome, which is something like that, many lamellas, and they are quite large in the range of few micrometer in size. The nano are not going well. Let's go into the problem. Actually, if we zoom now, you have here this is the kind of the hip that we want to look for, the area. And you can see that actually, if we now doing a zoom, we can see here the bonds, and we can see here the synovial fluid, and there is a membrane that actually protecting the synovial fluid. And this membrane, the synovial membrane, has in them pores in the size of about 200 nanometer, 250 nanometer. People argue. So every particle that will be smaller than 250 will escape very fast from the synovial fluid. So if you have particles which are larger, like the large liposome that we are using, they will stay here much longer. So that's one good reason why we decided to use the large multilamellar liposome. You can see all this, all the structure, and I'm not going to elaborate more of this, but this was the point that I want to stress, the size related to the synovial membrane. That's how the experiments are done. We're getting from healthy people that have hip replacement, people that have car accident, or they have some other things. We get the piece of bones from them after getting the Helsinki to get approval together with the cartilage, and we cut a kind of a disc of cartilage, and we connect it to some kind of a system that you will see in a minute. We have an upper part and a lower part. So, okay, this is the way before we did it for the friction, and for the wear, because in the wear we're doing a lot of movement back and forth, like trying to imitate walks of 100 kilometers or 50 kilometers. So we have to do, then we take it together with the bonds and we attach it. So basically it's similar system, but it's done a little bit differently in the practice. And this is the system we are using to measure. So what you have here, you have a water bath. In the water bath, you have a kind of a stable stage on which you can attach one of the discs, the larger disc usually, 8 millimeter in size, and this is a moving part. To the bottom of it, we attach the other disc, which is about 4 millimeter in size. We can apply different level of forces here, of anything that we want. You can see the numbers in a minute. All this is embedded in a fluid, any fluid we want, of course, aqueous fluid, and it can contain the lubricant or without the lubricant, synovial fluid, and other things that we want to do. We can control the temperature. We can take samples all the time and check what is in, and this is the system, and there are 2 papers that published this year that describe the study we did. One of this is on the friction, and this is on the wear. So actually, just to show you one experiment, the trace of the paper, this is a friction experiment. So what you do, you start moving this, and at the beginning there is resistance, then you start it start moves, and here at this point where it turn, this is from here we can measure the friction coefficient, what called the static friction coefficient, just because before it start moving, and this is the dynamic while it is in the motion itself. So we get 2 parameters, the static and the dynamic friction coefficient, which we can get them under many different conditions and many different lubricants and other factors that we have in this system. A very, very easy, very, very simple system. And for the wear, we're doing exactly the same, except that we do many more motions. And what we do, we measure the amount of small, very small particles that, due to the friction, are really removed from the cartilage, and we can determine them either as collagen or as a proteoglycan. So both are equivalent, and you'll see the data before. The first thing we wanted to know is which liposome to use, which size. And we already knew that the dimeristoyl has a phase transition of 24, and we expected it to work for us. So we tried it, and we took the large multilamellar liposome and the small unilamellar liposome. We applied them in the system. We put some pressure, and then we took the cartilage piece, and we actually, with the microtome, we sliced this to small pieces. Here with this is the micrometer, and we check the amount of phospholipid of the DMPC that is along the z-axis of the cartilage. And what you can see, that the SUV is going deep inside and nothing stays on the surface, which is here, while the large liposome stay very close to the surface, and very little only small fraction of them go deeper. And this small fraction is mainly small amount of small liposomes that are present in the big preparation. So they perform very, very differently. The large one remain close to the surface. The small one really go inside the cartilage itself. Why it's happened? Because this is the structure of the cartilage. It's actually a kind of a cage composed of collagen fiber, proteoglycan, and a water gel. It's a hydrogel. So when you press it, it goes through, and because the particles are very small, they can just escape. And if you put more pressure and wait more time, they will go down, and because the membrane below, if you remember, has a hole which is 250 nanometer pore size, all the lipid will not stay here, but disappear and will be effectless, as I'll show you in a minute. This is the composition, by the way, if you want to know it. So these are the data of the friction coefficient. We have the static. This is the static, always higher, and the dynamic. And you can see very clearly, this is in saline. It's not a good solution. This is in synovial fluid, normal synovial fluid. It's quite a good lubricant. This is inflamed synovial fluid. It's worse than it is here. And now we can start playing with the different lubricant. You can see that the small unilamellar liposome doesn't do us any good. You can see it if we take the DMPC with cholesterol, large vesicles, it doesn't do us any good. If we take the DMPC MLV, the large one, this is DPPC MLV, it's worked better than the synovial fluid, but not good enough. This phase transition is about 40 degrees and so on. And you can see here that the DMPC and a mixture of DMPC with some DPPC are working the best. Quite a dramatic change in the friction coefficient. Actually, it's a very, very efficient. If I put it here, HA, which we did, and I didn't like to put it here, because I'm always afraid of argument that I didn't do it on the right condition and so on, you can find that the HA is doing a little bit, not much, actually worse than the DPPC, even in the optimal amount. So that's what I told you. Then we tried to look for the wear, and the wear is much more complicated issue. How to measure it? Can we look at change of morphology? We tried, but it was impossible to quantify it. We know that wear increases with increasing normal load and with the test duration. The more you walk, the more wear you see. I have to say that all the wear that we see is less than 2%, less than 1%, very, very small. The cartilage is a very, very robust tissue, so the wear is really small. So, so basically, we decided to follow the collagen and the proteoglycan through the amount that is actually shaded into the solution, and that's what we did, and I'll show you some of the data. We apply a huge kind of spectrum of pressure from 0 to 60 Newton, and a walk from 0 to 50 kilometers in this trial. And we did the analysis, and you can see the data now.